Good morning, good afternoon, everyone. Thank you for attending Cambridge GaN Devices tutorial webinar series. I'm Wei Yipan, Digital Marketing Manager of CGD and your moderator today. I'm honored to invite Mr. Zahid Ansari, Vice President of Operations at CGD, to give this speech. This is the third webinar in our tutorial series. During this series, our GaN experts share their insights on gallium nitride, a kind of wide bandgap material, enable high switching frequency and higher power density for efficient power conversion. We have hosted 2 webinars in February and March. The first one was presented by our Chief Commercial Officer, Andrea Briccani, focusing on the advantage of GaN compared to silicon. And the second one was hosted by our CTO, Professor Florin Udrea. He introduced state-of-the-art architectures and future concepts in GaN technology for power electronics. Both webinars are available on our website and CGD's YouTube channel. From this webinar, we will give you more insights on CGD's high-voltage technology ICeGaN and how it enables ease of use while not compromising superior performance of GaN. We will have the 4th webinar on May 24th, presented by our Director of Applications Engineering, Peter Kaminsky. Please stay tuned. Please make sure your microphone is muted while our presenter is presenting. If you have any questions, feel free to post them in the chat box. After the presentation, a Q&A session will follow. Now the floor is yours.
Good afternoon, good morning, and good evening to all of you, depending on the part of the world that you're in. Thank you for taking time to attend our webinar. So I'm Zahid Ansari. I'm responsible for operations at Cambridge GaN Devices, where I have been since the beginning of 2019, when I joined the founders and the small team we had at the time, with the goal of helping build a business here. So my background is in electrical engineering with a specialization in semiconductor physics. I started in the industry some years ago when I joined Fairchild in 1980, and since then have worked in various roles, including design and manufacture of silicon, gallium arsenide, and GaN ICs, and also of electronic systems. I've had over 15 years of experience in power electronics, having worked on manufacture of control ICs for AC to DC and DC to DC converters, and also in manufacture of actual motor control inverters. I've been working with startups for quite a while, since about 87 actually, and have had some experience taking companies from sort of startup concept to volume production, with one of them going to over 100 million units a year for ICs and for controllers. So it's been a pleasure being part of the CGD team. And what I'm going to talk about today is to give you a quick, brief introduction to CGD, some high-level introduction to our ICeGaN technology, and then go into a description of some of the key building blocks and how, when we first designed those building blocks, we designed not just for the ease of use and functionality that we were targeting, but also for robustness and reliability. And then I'll also try and give you some perspective on some of the processes and systems that we have put in place with the goal of improving quality and giving us tools for continuous improvement. So Cambridge GaN Devices was started by Dr. Giorgia Longobardi and Professor Florin Udrea in Cambridge University. It was incubated in the university and spun out from there. And they established it with the goal of making gallium nitride power conversion ICs easier to use, thereby accelerating the adoption of GaN with the objective of reducing energy waste. So basically making power converters more efficient and thereby reducing energy waste. So since the early days, we have expanded a bit. So today we operate in 5 different locations globally, and we have a team of over 45 people. We're bringing very experienced perspective as well as great sort of diversity to the company, diversity of knowledge and perspectives. And we are we are all motivated by the fact to try and do our bit to help with climate change by reducing waste of electrical energy, and to do so by exploiting sort of the knowledge that we have in the team to deliver innovative products that help with sustainability and our responsibility to the planet. So to do that, we introduced our products that incorporate our ICeGaN technology. What this does is sort of builds on some of the capabilities, manufacturing capabilities that already existed, but adds protected components to it that allow us to deliver differentiated product that solve a customer's problem and make it easier to use GaN. So, GaN devices have been around for a while. And if you look, initially there was just sort of the discrete temp devices and cascodes where you had normally on transistors that were gated by a silicon MOSFET. And then the next generation of GaN ICs that came to the market actually incorporated gate drivers and extra functionality into the IC. It was our view early on from our perspective of market that there were some limitations of each of those solutions. And the goal was to deliver GaN ICs that were as easy to use as silicon. So it would reduce the barriers to adoption and to improve the reliability and robustness of the devices, thereby enabling customers to design power supplies using GaN that were reliable and achieved energy saving. So if we look at that, then our products are essentially a single chip IC where there is a gate pin that controls the 650 volt power transistor, and that can be driven by any gate driver circuit. So as opposed to the integrated gate drivers, here you can basically use a gate driver that was designed to drive a silicon MOSFET or a silicon IGBT and connect it directly to our ICeGaN chip. I'll be going into a little bit more detail about some of the building blocks that we have in there. But if we sort of look at it, there's ESD protection on the pins, and then there's some analog building blocks as well as some logic functions that enable us to control and protect the power HEMT and also provide feedback to the system in the form of a current sense output. So the ICs incorporate ESD protection. They incorporate gate voltage clamping that provides higher threshold voltage to the outside world, which allows people to use higher gate drivers that have higher operating voltages, and also improves the robustness of the gate pin. And then, Miller clamp and logic circuits that are designed to help ensure that the device turns off properly and stays off under conditions that it would the IC could see in the system. And at the end of it, deliver a high efficient solution. So, as I mentioned, we have sort of designed the building blocks for reliability and robustness, and I'll be talking through some of them one by one to give you some context for the approach we took and the solutions we developed. So some of the key features that I mentioned earlier was sort of the high threshold voltage. There's a voltage limiter which protects the gate. There's a Miller clamp device that is designed to control the off state of the power transistor, and ESD protection blocks. And these were designed for ease of use, but in the process of designing, we also designed for system level reliability, so accounting for abnormal conditions and normal operating conditions that would occur in a system. Component level reliability, and by that I mean the reliability of the IC, of the ICeGaN IC, and also for robustness to deal with transients and other abnormal conditions that you can have in a power converter. So the first piece of that is high threshold voltage. And so if you look at a conventional GaN HEMT, in enhancement mode GaN HEMT, you have to keep the gate voltage at 6 volts or below in order to prevent the device from getting damaged. So that is what has resulted in historical data sheets for GaN devices saying keep the gate voltage at 6 volts or below. And also, in order to ensure that the device stays off, in some cases, particularly in higher power applications, you have to take the gate negative to prevent it from accidentally turning on. So in the case of ICeGaN, the auxiliary HEMT devices that are shown in the box there are ones which basically take the extra voltage, so they can, since that's not going to the gate of those devices, they can withstand the extra voltage that we are seeing. So we can put a higher voltage on the external gate, which does not get seen by the power HEMT. So to go into a little bit more detail of the actual data on that, so the red line here represents the transfer characteristic of a typical discrete GaN device. So your gate voltage can go between 0 and 6 volts. And the threshold voltage is typically around 1.6 volts. So there are two implications of that. One is that your threshold is actually very close to ground, which means if your gate driver is only going to 0 volts, under transient or noise conditions, you can accidentally turn the transistor on. So that's one of the hazards that people solve by going to a negative gate voltage. The other is that the gate input needs to be kept below 6 volts, which means you are constrained in the gate driver circuits that you use. So either you use dedicated gate drivers that were designed to work with GaN, or you end up with several extra components on the outside in order to ensure that the gate voltage range is within the constraints of a discrete GaN device. So in the case of the CGD ICeGaN products, we address both of those problems. So one, we can accept gate voltages of up to 20 volts on the external pin, which allows you to use normal gate drivers that have been designed for silicon MOSFETs. The other is we've raised the threshold voltage from 1.6 to 2.8 volts, which means you've got a lot more noise margin to deal with DIDT noise associated with parasitic inductances in the system. So combination of those two results in improved system reliability by having the ease of use of the higher gate voltage and the higher threshold voltage. So one of the other key blocks is the voltage limiter. And this again is designed in the context of ensuring reliability of the power HEMT. So essentially the way it works, it controls the gate of the auxiliary HEMT, and that prevents the gate of the power MOSFET from going to more than the voltage limiter voltage minus a threshold voltage. Now, there's actually a bit more subtlety to the design than that, which I'll be going into in a little bit more detail. But as a measure of the performance, what this shows is actual, measured data of how when the external gate can go all the way up to 20 volts, the gate of the internal power HEMT, which is the one that you're trying to protect, stays at 5.5 volts or below. So essentially we have protected the power transistor with a combination of the auxiliary HEMT and the voltage limiter. There's another feature of the voltage limiter, which again was designed exploiting the GaN reliability knowledge and expertise that we had at in the CGD team. And that is related to a specific failure mechanism that is one of the dominant failure mechanisms in BGAN HEMTs. So this has been known for a while, and one of the papers that discussed it in detail was the J. He paper referenced here, which is sort of a group in Hong Kong that published it in the IEEE Transaction on Electron Devices in 2019. And that is that one of the dominant failure modes of BGAN HEMTs is time-dependent Schottky breakdown, which is very unusual compared to most reliability hazards, in that it's actually worse at low temperature than it is at high temperature. So what we did was we exploited that by or took advantage of that by building in a temperature coefficient into the voltage limiter. So we actually provide lower inner gate voltage at room temperature and cold than we do at 125 or 150 degrees. So the curve on the right is actually measured data going from minus 55 to 150 degrees to show the temperature coefficient. And the thing that we achieve at the same time is, given that the RDS on, or conductivity, if you want to think of it as that, of a GaN device, just like with silicon MOSFETs, is better at low temperature. We actually can reduce the gate voltage without compromising performance. So the RDS on at low temperature is not compromised by the fact that we've applied lower gate voltage at low temperature. So this is sort of exploiting our reliability engineering knowledge with GaN device knowledge to optimize performance while improving reliability. So the combination of those two, which is the auxiliary HEMT and the voltage limiter, actually has some additional benefits. And that is in further enhancing the robustness of the device and protecting against abnormal transients on the gate pin coming from the outside world. So this is a paper that was published or presented by a group from Virginia Tech at APEC last month. And what the Virginia Tech group does as a way to characterize gate input robustness is they subject devices to short transients of successively higher voltages up to the point where the hemp gets damaged, so the device is not functioning properly anymore. The curve on the left for a 16 nanosecond transient pulse represents our CGD device. The one on the right is a commercially available discrete GaN hemp manufactured on the same manufacturing process. So both of the 650 volt devices are manufactured the same way, but our product for a 16 nanosecond pulse, we can handle short transients of up to 78 volts compared to 26 volts for the discrete device. And for a 20 nanosecond pulse, again, we can withstand 66 volts compared to 24 volts for a device manufactured on the same process. And that's because the auxiliary hemp, the voltage limiter, and to a little extent the ESD circuit are protecting the gate pin and preventing the GaN, the power transistor, from seeing much of the energy in the transient. Next piece to talk about is the Miller clamp. So this is basically a transistor that is actually a proprietary layout and design that sits right adjacent to the power hemp. And an implication of that is that there is no lead inductance, so no parasitic inductance of significance between the source of the Miller clamp and the source of the power hemp. So if you've got current transients, they do not affect the gate voltage of the power hemp. The bits that are sort of grayed out are some of the things that provide some of the power to the logic signal and the logic inverter, but they are sort of secondary to the purpose of this discussion. And the impact of the Miller clamp then is it provides much better DVDT and DIDT noise immunity. So the plot on the left here is showing the response to a voltage transient, and the one on the right to a current switching transient. And what you find is with the Miller clamp, the gate voltage that you get on the transistor is much better controlled, so you do not get the ringing of the same magnitude that you do in the absence of the Miller clamp. So that sort of results in more reliable switch off and ensuring that the device stays off under transient conditions. So it's sort of addressing system reliability, which actually then also has an impact on product component reliability. And of course, there's the power hemp. You know, that's sort of fundamental to our GaN IC. So we did pay attention to the design of that, and we have used our expertise in design of high voltage semiconductor devices to ensure that there is significant margin on that device. So the devices are rated for 650 volts, but this is representative of a typical device where we've tested hundreds of them to the point of destruction to get an idea of how much design margin we've got. And the device is rated at 650 volts, but it does not break down till typically greater than 1200 volts. So this does result in robustness to transients on the drain. It also results in process margin to allow for variability in the manufacturing process. And here the green line is at 25 degrees and the red one at 150 degrees. The other thing that we have put on the device is ESD protection and we've got ESD protection on the VDD pin, the gate pin, and the current sense pin. And all of those, for all of our products, we achieve 2 kV human body model ESD. So we've had that tested by external labs, and all our products meet that spec. So, and to put that in context, there are GaN devices out there that are rated at 500 volts and some at below that. So, and that translates into potential hazards during either the handling or manufacturing process that can result in latent reliability hazards in the end system, and in a bad case, actually damage to the device, so it doesn't even function in the end system. So, so our products do meet 2 kV HBM. So one of the other things I'm sort of talk a little bit about and give you some context for is how we went about designing some of our processes and systems to give us information that is useful for quality and quality control and for continuous improvement. So back in early 2020, we implemented 2D barcodes on our DFN devices. So all of the devices that we have manufactured in the last 3 years have actually had a unique serial number. So this is the level of traceability which, if you're doing complicated ICs and CMOS processors where you've got non-volatile technology, you can use the non-volatile memory in order to store a number. And as long as the chip doesn't die, you can read it out. But if the chip dies, you can't read it out. So here we've actually got a unique serial number that is printed on the IC. And in conjunction with that, we worked with our assembly partner to have an assembly process that maintains traceability of the fab lot, the foundry fab lot that the wafer came from, the specific wafer number within that fab lot, the position on the wafer, so we can tell whether it's a center die or an edge die, and if so, how far from the edge. The lead, and also traceability of the bill of materials used to manufacture the package. So for any of those parts made in the last 3 years, I can tell you, what lead frame lot number was used. And every lead frame has a barcode serial number on it. I can tell you which lead frame strip was used, the position on the lead frame that particular chip was in. So is it always, the top left IC on the lead frame that has a potential quality issue, for example, and also the order of processing of the die. So which die got picked up first and put down onto the lead frame, and which one got put down after that. So all of that's sort of well and good as long as you can, access the information. So what we also did was we put systems in place to allow us to have instant access to that information. So in our intranet, we've got a web server where we can basically go in and enter the serial number, and we get a lot of details about the IC. It shows us, where on the wafer it was, which wafer, which shot. So since you've basically got a stepper that's repeating a pattern across the wafer in the process of printing it, it tells us which shot, which position in the shot. So we can also, for example, see patterns, like is it always the, cornered eye in the shot that has different characteristics from the others. So this gives us valuable information. And, if I compare to what is common in the industry, if we look at sort of the three major operations, if you want to think of it that way, there's the sort of wafer fab, there's the assembly or the packaging of the device, and then there's the test. So if you take a look at a packaged part, take a IC off of a reel, or look at an IC on a printed circuit board, typically from the number that is printed on that IC, the supplier can go back and tell you which wafer fab lot it came from. It is generally not possible to tell you which wafer within that fab lot it came from. So in our case, we can tell you which wafer fab lot, the wafer number, and where on the wafer that particular IC was manufactured. At the next operation for assembly, typically from that marking, you can tell the date code and the assembly lot. So you know when it was made, and by going back and looking at the travelers that the assembly house has, you can get additional information from related to the assembly lot. So in our case, we have the date code and we have the assembly lot, but we also have all of that information about fab lot, wafer number, position on the wafer, the unique strip number and the position on the strip in order of processing. So when it comes to addressing quality questions, we have much more information to work with. And a test, as you would expect, we keep track of test lot IDs, the test date, test program, yields, etc., that are common in the industry. So all of that, if we sort of think about some of the benefits of it, what it means is we have full history of ICs available for our continuous improvement. We've also integrated the manufacturing data with our characterization databases. So we have highly automated systems for doing device characterization, where the characterization results go into databases in the cloud, and we have web front ends that allow us to access that information. And then we can go back in and get history of that product simply by going to another tab and using the same mark ID in that tab. So this also then helps us when we are doing characterization of new devices in the R&D process, and gives us much better characterization information before we release products to the market. And if and when we have problems, it gives us tools that allow us to be much more rapid and effective at problem solving. So it is, from one perspective, a fairly simple thing when you sort of just look at it. Okay, it's just a number printed on it, but there's actually a lot of infrastructure behind it and a lot of automation to make sure it is robust and works well. So if we look at the product portfolio that incorporates all of these features, last year we announced our H1 series of single chip E-mode devices, that all of which were 650 volt rated with 750 volt transient capability on the drain. We have devices that were between 200 milliohms and 55 milliohms for RDS-on rating, which support peak currents of max currents of 8.5 to 27 amps. All of these are capable of being driven by standard gate drivers with up to 20 volts on the gate. And they come in industry standard packages, which is DFN 5x6 and DFN 8x8, depending on the RDS-on rating of the device. And they also all incorporated the current sense feature. I think Andrea in an earlier webinar had gone through more details about the functionality of those devices and the features of those devices. So I'm not going to go into that here in detail, but they're all compatible with standard MOSFET drivers. In addition to the products, of course, there's a great deal of sort of support material and collateral that we have available. So these include sort of application interface boards, which they allow customers to test our devices, in effect matching the footprint of another device to do the first level of evaluation, though generally you've always got the opportunity to do further optimization relative to using it in an application interface board. And then there are also sort of white papers, application notes, design guides, and user guides that are available from our website or by contacting our sales organization through info@GaN Devices. So we are going to be at PCIM week after next. So where we will be showcasing some of our future products. So there's going to be information about our sort of expanded product portfolio presented there. And there'll also be some of the latest demos at the booth. So if you are at PCIM, encourage you to sort of stop by Hall 7, booth 372. Our CTO, Andrea, is also going to be presenting there. So there's an opportunity to hear him and see him and meet him on the 11th. So in terms of review, if I sort of just go through what we've gone through today, I've given some perspective on ICeGaN technology, sort of introduction to the main building blocks. I've spoken about sort of design for robustness and reliability, about how the ICeGaN features deliver not just ease of use, but also reliability and robustness. And spoken about some of the systems and processes that we put in place very early on in the company. So when we first started R&D, planning for quality information, and I've sort of told you about our presence at PCIM. So thank you. I think we are open to questions, if you like.
Thank you, Zahid. Thank you. It's a very informative presentation. As Zahid said, now we are open to questions. And if you have any questions, please post them on the chat. Now we receive question from TY Su. Hi, CGD team. Are there any benchmark with other competitor about GaN device performance? Because there are many similar products in the market, and I would like to know the difference.
Yes, there are. So I think for a number of applications, we do have performance data for various topologies and configurations. I mean, as an ops and manufacturing guy, I'm probably the wrong person to answer that question openly. So, but we can definitely put you in touch with someone in sales and marketing that could help you with that.
And just to add one more comment, maybe you could also stay tuned with our next webinar where we will touch more upon on our ICeGaN applications.
Yeah, so I think Peter at the next webinar is going to be talking about the ICs in the context of applications. So there will definitely be more information on that there.
Thank you for this question. As we are waiting for more questions, actually, I have a question for Zahid.
Oh, no.
Because I know that when I joined CGD, I already know Zahid is one of the oldest staff at CGD. By oldest, I mean the number of years he has stayed with CGD. Yeah.
I think I might also be the oldest, but
Well, okay. If we go back to page 25.
yeah. Yeah.
Yeah, about the 2D barcode. When I first learned about it, I was quite amazing. I wonder what made you propose this idea?
You know, as a manufacturing person, because, you know, I was a design guy many, many years ago, but today I'm really a manufacturing person. It is important to have access to history so that when you're trying to optimize a process or solve a problem where you might have some defective devices and you're trying to determine what might make them defective, having detailed information is valuable. So what this basically allowed us to do early on when we were doing R&D was it allowed us to assemble parts. And when we tested them, we could tell whether it was, you know, a die at the edge of the wafer, or whether it was the center of the wafer, which wafer it came from, things like that, which historically would not have been available. So what that allowed us to do was, from a packaged part, know whether there was wafer-to-wafer variation or within wafer variation, things like that. So that's sort of um, the production engineer in me that um, figured it would be useful, and we worked with our assembly partner to put the systems in place. And then internally, we put the databases and everything else around that in place.
Because to me, it's like a GPS system just for the chip, not for people.
Yeah. So do we have any other questions?
Yes, please. I think TY has one more question.
Okay.
While waiting for TY's question, Raf has another question. How many CGD devices are in the field? And how many field failures do you have?
So far, we do not have any field failures. So we've not had any RMAs to date. In terms of the total quantity out there, I don't believe I can comment on that at the moment. There's some, it's.
And Muhammad Zhu, thanks for the presentation. I would like to know how much area is used to integrate all of the functions you described, and how much is the specific RO degraded by this?
Well, we tend to think of it a bit differently in that the specific RON is based on the area of the power transistor, not of the overall area of the IC. But depending on the size of the transistor, the ICeGaN circuit doesn't increase much. So the area of the ICeGaN circuit doesn't increase much. So clearly it has, there's more area impact on a 200 milliohm device than there is on a 55 milliohm device. But it's so depending on the product, you're talking about in the range probably of 5 to 10-ish% of the overall area. So there is some overhead of the ICs, but it is still a small fraction of the overall area.
Thank you, Zahid. Jimmy Liu has a question. How about on-state resistance of temperature coefficient for auxiliary HEMT? Positive or negative TC?
The temperature coefficient of the auxiliary HEMT is actually similar to the temperature coefficient. It is just a GaN HEMT, so it's similar to the temperature coefficient of the GaN HEMT. So the trick then is to basically make sure that the temperature coefficient of the voltage limiter accounts for the temperature coefficient of the auxiliary HEMT also, to ensure that the inner gate voltage is at the designed voltage. I don't know if that answers your question. I hope it does.
For the presentation, I have a question. Is the current sense circuit in ICeGaN able to measure bidirectional current?
Yes, it is.
Short answer. Frank said, thanks.
You're welcome.
Yeah, we have another question from TY. Are there any successful story about designing to win with CGD GaN device? Where's fab of wafer?
Sorry, could you repeat the question?
Are there any successful story about designing to win with CGD GaN devices? And where's the fab of wafer?
So the fab of the wafer. So we use TSMC, which is the global #1 foundry in the world for our assembly, for our wafer fabrication. So it is on the most mature and the highest production GaN process available today.
First question is, any stories about if we win the designing?
Yes, I think there are. We do have design-ins and design wins of the GaN device. Some of them I cannot list. There'll be information on some of them at PCIM when we have the demos and reference designs there. But I do not believe I'm allowed to disclose the names of some of the customers that are using our product.
Exactly. We still have a few more minutes for questions. So I said, thanks a lot.
You're welcome. So, so thanks to everybody for taking time out of your days and evenings to join us. And I encourage you to attend the next one, where Peter will be giving you context for how CGD's ICeGaN products can deliver value in applications. So thank you and enjoy the rest of your day.
Thank you very much, Zahid. Hope everyone enjoyed this presentation. After the presentation, we will share the link to the recording and also the PowerPoints with everyone who registered. Please stay tuned with our social media, LinkedIn, Facebook, Instagram, Twitter, and WeChat if you have the Chinese social media. Thanks, everyone. Bye-bye.